Hey, all right. Welcome back. This is session 2, part 2 of our creating custom PCBs walkthrough. In this session, we're actually going to do the PCB layout. In the last one, we designed the schematic for our Klima board. And then after this, we're going to have a quick tutorial in how to assemble them, put them all together. So we're going to just get right into it. Let me switch over to EasyEDA, and here we are. This is where we left off last, and just a quick sort of intro. This is, again, where we're going to do our design. This is our tools, and then these are layers and objects, and this is kind of a super important thing. This is where we can look at our top layer, our bottom layer, silk layer, which is where labels go, etc. And then we're going to look at this stuff a little bit later. The first thing that I want to do is I actually want to, this grid style just drives me nuts. So I want to change it to dot, and oh, so much better, so much cleaner, much easier to see. The next thing is that EasyEDA automatically puts in what it thinks is going to be your sort of minimum, or a guess as your outline, and this, where all your components would fit. And I'm not sure how it calculates this, because this is obviously very large. And I'm going to delete that because we have started with a Meadow wing. And when we imported the Meadow through-hole wing symbol, it automatically came with this footprint, which already has the wing outline. So it's a nice shortcut. So we're going to use that as the outline. And then the other thing that I want to talk about a little bit is our grid. Now, when you first come in here, it probably will say units millimeter. And the grid size will be a little bit weird. It says 2.54 millimeter and 0.127 millimeter. And that's a little bit, those are weird. That's a little strange size. And that's really because of legacy reasons. Electronic design was really, was really invented in the United States, and the United States uses inches. And so if we switch over to mils, you see that's 100 mil and 5 mil. And mils are thousandths of an inch. So if you look at breadboards, they're, or these headers, each one of these are 100 mils or 1/10 of an inch apart. And so that is, unfortunately, just kind of the standard size of a lot of things. So when you're laying out components, you'll often work in mils, but then when you're working on your outline of the board itself, I often switch over to millimeters because I like to design my enclosures and my products in metric. Otherwise, it's really hard. No one likes to work in imperial. It's just silly. So anyway, I want to modify this. I'm going to do grid size is 100, but my snap size I'm going to change to 10, and my alt snap is going to be 5, so that's good. And then I'm going to align this. I almost always do this. I align my bolt to the origin. And then this just gives me a nice way to sort of measure everything off of your bolts. And again, this is a product design thing. And the first thing that we're going to do is we're going to lay out our components. And this is generally when you're doing your PCB layout, that's the first step you do. And you start by laying out the most important components, or the components that have the greatest constraints. Like for instance, let's say this was a chip that had USB lines. I might lay this out somewhere right up here, and then I turn it so that the USB lines went to the USB connector. And then what you do is you lay out the components that are supporting those important components, and then you work from there. When we go to route, it's the same sort of thing. Now I know that this thing is going to go up here, so I want to put this here, and I know that it goes this way. This is the back end of this connector. So I'm going to put this up here, right on the edge. That's my solar panel connector, and maybe I want to just move it down and get a little more headroom up here. And then I'm going to place my BME 280 sensor. I'm going to have it directly in the middle of my board. And I'm going to align it kind of near my I2C stuff, just for the heck of it. Now, I also want to align it. I want to think about the routing a bit when I align this. And you can see the clock goes here and the data goes here, and they would cross over. So I've got some options. I could turn it this way, and then I could run lines underneath. Or even better yet, I can turn it this way. And now when I route, it's going to route, they'll route, you'll see, much easier to route it. Much easier to route it this way, even though I'm making a mess of it there. So we're not going to route yet. We're just going to place some components. So the next thing is I've got my pull-up resistors for I2C. And you can see there's these blue lines. These are called rat lines, and these show unconnected things. And the first thing I want to do with these is there's a lot going on. So I can go over to Design Manager, and I can see my nets. And I'm going to hide the power and ground. And that, all of a sudden, see, that is a lot easier to understand. And we're going to route power and ground last. And they're basically, everything has power and ground. If you have those rat lines shown, then it makes a mess of things. So let's first get our resistors in place. So this is the data resistor. I hit space to rotate, and I'm going to put that one here. And then I'm going to turn this one and put this one. That's the clock line. And so now the line is going to go right through. And the next thing I'm going to do is I'm going to line and size these labels. These are really big. I don't like them that big. They take up a lot of space. So I'm going to change this to Demi Light. That makes them much smaller. Rotate this one and change to Demi Light. Great, and let's do the same to this one. Cool. Now we want to place our capacitors. Now recall from our design, these decoupling caps, C1 goes to 8 and C2 it goes to 6. We want these as close to those leads as possible because we want them to dump their electricity into that component before dumping it into the rest of the board. So C1 goes to 6, so we're going to put the 3 volt 3 and 3 volt 3 right next to each other. And we're going to line this one right next to it. And then again, let's change these to a smaller font and rotate them and place them in a reasonable place. Now, one thing to note about these prefixes is that you generally want to align them. You want to align them all in one or two directions, which means that they should all be facing this way or like this way. And what that means is that when you're looking at the board, you only have to rotate it once to read any prefixes. Ideally, they all point the same way. So you don't have to rotate it at all. You just keep it in one spot. It's not always practical on very complex or dense designs. Okay, so we got that. And then this one has a prefix. And you know what? I know what this is. I don't actually want to bother putting a prefix on the board for this. It just feels, it feels like too much. Also, something that you notice, I keep accidentally selecting this board, and it's really easy to like, oh, I moved it around. So one thing that's super helpful is to lock it. Right click and lock, or go over here, select it and say locked yes. And now I'm not going to move it around. And there it is. So I'm going to select this, and I am going to say, no, don't display the prefix. And the same on this one, because even though it won't show up anywhere, I just don't want it there. Just a, I guess, OCD maybe. Okay, now I need to actually route the traces. I need to actually connect everything up. And again, you do your most important lines first. So in this case, there's not actually a lot of stuff going on here, but if we had other supporting components out here for this BME 280, I still want to do my bus lines first. So I'm going to hit W or select this line, this track here, track or wire, and then I'm just going to select it and then route it over like so. And there's two to think about when routing. The first is electricity is like water. You don't want to make a river that's a 90-degree angle. And this, the reason why is that when the electrons come pushing through here, they kind of hit this wall and they crowd up over on this corner and they're not here. They like 45-degree angles or even rounded stuff. So this is much better than that. So don't do 90-degree angles. The other thing to know is that you don't want any acute angles either. So let's say that this actually had to go to another I2C device. 90 is okay here. This is not okay. And the reason why is that if you're creating this PCB using acid etching, the acid will this will create an acid trap in which a blob of acid might get in here and get trapped and etch out much more of this than you want. The best for something like this is actually to do, you would do a line, you run that, and then help it out with a little 45 on each side, and that's a real clean connection. Obviously, we don't need that here. Okay, so that's routed. Now we're going to run our power. So 6-volt solar. So we're going to route this up to here and then route it to here. And one thing I want to do is that this is where all my power is coming in. I want to make this bigger. I'm going to make this 30 mils. And 10 mils is actually fine, but I like to overbuild things a little bit. And you can look that up. You can look up your, based on your copper thickness, these are going to be 1 ounce, what they call 1 ounce copper thickness, which means every square inch will have 1 ounce of copper. That's how thick it is. You can use ½ ounce copper. That's another common one. But you can look up on the internet like how much power can be moved over what size of trace for your copper thickness, if you want to be real technical. But for me, this is totally fine. Even a 10 mil would have been fine. But it is nice to beef it up. Okay, cool. So our routes are in. We didn't use the auto router. That will only make a nightmare of your design. And we've got everything routed except for ground and our power. So I now displayed those nets, and you can see, oh yeah, I still got to route those things. But we're going to do something different for those. We're going to do a copper pour, which means we're going to fill all this rest of the area with copper that's going to be ground or power. And we're going to put a power plane on top and a ground plane on bottom. And the reason why is you always want a ground plane opposite of your components. And this will become more apparent later on when you start doing controlled impedance and whatnot. But basically, the ground plane underneath serves as kind of a sink for errant signals and things like that and capacitance. We'll explore that in a more advanced tutorial at some point. But just know right now you're going to do on a 2-layer board, it's going to be ground on the bottom and power on top. And that brings up another thing that we should talk about is multi-layer boards. Most of the boards that you spin are going to be simple 2-layer boards. That means they've got a fiberglass core, and you've got copper on top and copper on bottom. And the copper is what constitutes a layer. And that's where your signals and your power and stuff is routed. Now, some boards are very complex, and the routing requires multiple layers, and either because there's controlled impedance or because there's just not enough room on the layers for all the routing, because there might be a lot of signals. The Meadow board, this is Meadow Core Compute module here, for instance. This is an 8-layer board, and it has controlled impedance and high-speed signal routing and stuff. It's very complex. There's a lot of design considerations that go into this little thing. You don't have to worry about that generally when you're designing a breakout module for a Meadow or most of your IoT designs. However, if you need to do that, if you need to do more layers, it's pretty easy. You go up into edit, where is it? It's in the layer manager, tools, layer manager, and then you can add additional layers. So you can add inner. If you go to 4 layers, it'll automatically add an inner 1 and an inner 2, and then you can go additional layers, 6, etc., and that adds additional layers. We're going to keep it at 2, and it's just going to be top and bottom. So what we're going to do is pour our copper area on the top. It's going to be power, so we're going to choose 3 volt 3. Make sure we're on the top layer. And then outside here, I'm going to start this, and this makes it easier to select this layer if it's on its, if I put it, I could put it right on the outline here, but it would be hard to select. I'd be selecting the other board. And then 3 points, and then right click to close. There's my 3 volt 3 power plane, and notice some of the rat lines disappeared because they're now connected. And I want to show something real fast. So first of all, because I put this out here, it's easier to select. I'm not competing with selection for that. But if we look at these connections, you'll see something interesting, that they're connected via these spokes. And that's something over here. It's a pad connection, spoke, or direct. And if you look at direct, like, oh man, that looks a lot cleaner. But in fact, you want spoke. And this is really what these are called, are thermals. I've never heard of spoke before, but they are thermals. And that's what you'll find in other EDA tools. They'll call them thermals. And what that allows is a good electrical connection, but it won't sink a lot of heat away. And so when you're assembling this, this will prevent problems during the reflow process, where there's differential heat thermal properties on a component, and like a capacitor might tombstone. That's where it stands upright instead of laying flat. So this prevents that. It also makes it easier to solder. For example, let's say we were actually having to hand solder this. If this were a direct pad connection, it would be very difficult with a soldering iron heat this up enough to actually get solder to melt, because all the heat would just be flowing out into this big solder, or the copper pour. So we want a spoke or thermal connection. The other thing is islands, and we'll show that in a sec. One thing that I forgot to do is route the rest of our I2C. And this is a good thing to see. Notice that these wound up being really big, and that's because the last thing I selected, or last thing I wired up, had a 30 mil route. And you'll notice that these are now conflicting with that pour. So there's a couple things that we want to do here. One is we want to reflow the copper so that it's not in the way. The other thing is that when we're actually doing this, it's nice to, once you have a solid region poured, it's nice to turn that off, the visibility, copper area. It's nice to turn that off so that it's not, so visually you can still route and whatnot without it sort of being in the way. Visually in the way, it's still there. But we need to reflow this copper around those lines. So we can either right click and unselect everything, and right click and say rebuild all under copper area, or Shift B. Shift B is your friend. That will rebuild. And this brings up one additional thing, which is on this copper area, you have an option for keep island, yes or no. An island is an unconnected area of a pour. And that looks nice, but when you're doing complex boards, sometimes you'll see like a rat line between, like two things that are 3 volt 3, and you're like, I don't understand, why is that not connected? And it's because that's actually an island and they're not connected. So it's nice to turn that off, and then sometimes I'll turn it back on when I go to make this, just because it looks kind of nicer. But there's no important difference there. Cool. All right, so we've got our power plane drawn, but we still got to do our ground plane, and ground's going to be on the bottom, so we need to switch over to the bottom layer, and we can select this, or we're going to hit B to switch over to that. T for top, B for bottom. And again, we're going to grab a copper area, or we're going to select E for that tool, and hit ground, and then again, we're going to pour this out here, and I'm pour it outside of the other one so I can select it without competing for this with the selection of the other one. And I make these, I'm starting from the top out, and I just make them, you know, concentric outlines. And that makes it easier to know what's going on. So that's poured, and we're on the bottom layer. That's what we're looking at. We're going to switch back to the top, and now we need to connect our grounds to that bottom layer. And for that, we're going to use a tool called a via. And a via is like a little tunnel. So you can hit this tool, or you can hit V. And I'm going to put this right here. And what that does is that automatically names my via for ground. And again, I'm going to go back to this, and I don't want to see the copper area right now. If I do a V without pasting it on, if I just put it out here, it's not named, and then I would have to go and manually name it ground. But by pasting it directly in first, then it picks up that name. So that's just a little trick. All right, so I've got these ground vias, and now I want to wire this up. So I'll wire this to here and wire this to here. And you might be thinking to yourself, well, you got one via here. Why don't you just connect them to? And that's totally fine for most things. And then not, you know, and not have this via, right? And that's totally fine for most things. It's not okay for decoupling capacitors, because it does, doing that, tying them together, can make some weird electrical capacitance that we don't want. And I don't fully understand what it does, but I just know that you don't want to do them. And vias are cheap. Vias are free. They don't add any money to your board. So you can put all the vias in you want. In this case, we're going to share. Those two can share, and we'll just tie them like this. If this board was, or if this component needed to dump a lot of heat, like maybe it was a power component, maybe it was converting power from a high voltage to low voltage, we might actually pour a solid area of ground and then do a bunch of vias. But in this case, it's not doing anything with heat. One is fine. And then we need to do the same up here. We need to put vias in for the solar jack, and just as before, because this is a power line, I'm gonna beef these up a bit. I'm gonna beef this up to 30 millimeters, or 30 mils, not millimeters. All right, so there we have it. We'll show our copper area again, and we need to rebuild. Shift B is your friend. And there we go. We're basically, where components are laid out and we're routed. And now I want to check to make sure I did everything all right. So I do design and then check DRC, and that runs through all these things. Let's also refresh our nets. It looks like everything has been routed appropriately. There's no design rule, DRC, design rule check. There's no errors on that. So our board is good. There's one final thing I want to do. I want to save often, actually. But I want to go to the silk layer, and I want to add some labels to this. So I'm going to grab the text tool, and I'm going to put a label there. And I'm going to change the font. One nice thing about Easy EDA is it allows true type fonts. You can go into fonts management. You can add fonts. And these are Wilderness Labs fonts, Mrs. Eves and Wave House. So I'm going to change that to Wave House. And I'm going to say DevCamp 21. And copy and paste. And I'm going to call it Klima. And then I'm going to version this. And this is super important. Putting a version on your board is really important, because when you're working with your board, you want to be able to just pick it up and know what version that is, because you might change the design, and if you don't know what the version it is, then the pinouts might be different, etc. So this is really important. So there we are, DevCamp 21 Klima V1A. So that is basically, our board is done. So switch back over to the deck. And we're going to talk through a couple more things. So in review, In terms of the rules, ground plane opposite of major parts. Remember, no 90-degree angles, no acute angles for acid traps. And 0603 is really the smallest part I recommend placing, because otherwise they're too small and it's just a nightmare for assembly at home. If you've got a machine or something that does the component placement, then you can use whatever size you want. And in terms of the process, lay out your components first, get them in the right spot, do your high value components first, and then the stuff around them. Hide those nets so that you don't see all the the power and ground rats. And then don't bother with the auto rotor. You can try it just to see how badly it will screw up your design. But really, I think of, this is kind of strange maybe, but I love laying out PCBs. To me, it's very meditative. And as you're laying things out, you're actually validating the design and you're thinking through things. The auto router sidesteps all of that, and you'll wind up with more errors in your design, but also the auto router just makes an absolute mess. It doesn't have any intelligence. Maybe as we maybe one day GitHub will do an AI auto router or something, and then the router will make sense. But right now, auto routers are terrible. Don't worry. Don't bother with it. But route your high value lines first, your buses, your differential pairing, etc. And then finally lay your planes and then do your vias to tie those things together. Now, once you've created a PCB design, once you've done the layout, it's time to order that to fabrication. And in order to do that, you actually output Gerber files, and those are drawings for each layer, and a PCB fabricator will know what to do with those to how to make a PCB from that. The first thing that I want to show is that if you're, and this is a nice thing about Easy EDA, is that if you're in Easy EDA, you can order your PCB directly from here. If you go fabrication, PCB fabrication, yeah, check DRC, there's no errors, and you can order directly at JLC PCB from here. And we'll talk about these options in a moment. You can either download the Gerber or you can just order straight from them, and then this will automatically bundle up the girders and will create a cart and will automatically add it to your cart and have everything, all the settings in there and stuff for you. So JLC PCB is fantastic for simple boards. They even have, you can even do multi-layer boards with them and stuff, but they're really quick turnaround, simple boards shop. If you're doing very complex boards, many layers, and you need to control the stack up and stuff, Rush PCB is a great outfit. They're out of San Jose and Toronto. And they do quick turn PCBs. And then if you're doing, once you start to do production run quantities, there's a number of suppliers. One that we have used with success is PCB Unlimited, and they're based out of Portland. But like I said, Easy EDA makes it very easy to actually order order them. Ordinarily, I hit an OK button, and then you'd see the cart come up, but for some reason it's not working right now. I'm not sure why. But a couple of things to note about that. I want to talk about the fabrication finish options. So when we were over in Easy EDA and we had the opportunity to order, it gave us a finish option, and it was either Hassel or Enig. And Hassel is a hot air solder. It's like an air knife. They blow hot air over it, and they put tin on or like kind of solder on top of the pads. And that used to be that used to be what everyone used, and that could make things easier to assemble. Enig is electrolytic nickel immersion gold, and that's a gold finish on the pads. And Hassel is definitely cheaper, and And there's 2 Hassel versions. So if we go in PCB Fabrication, you'll see surface finish is Hassel lead or rose, which is lead free. That's a reduction of hazardous substances directed, ROHS, pronounced rose. Always do lead free. Lead free Hassel or Enig rose are what you should choose almost all the time. We choose Enig almost every time, and Enig is arguably a better surface finish. For some components, like very fine pitch components, you actually need Enig. You can use Hassel, but it causes more problems. But Hassel is also a lot cheaper, and the finish looking is different. So this is a board that's finished Enig, and you can see all the pads are gold. I don't have a Hassel board, but the boards would come back with tin colored or silver colored pads. So yeah, Hassel, lead free, rose, or Enig. Whatever one generally for simple boards. For more complex boards, almost always Enig. And in fact, we don't order anything that isn't really Enig at this point. So with that is everything on the intro to PCB layout. And next up, I'm going to show you, okay, so we've ordered a board and they come back from PCB Fabrication. Now what do we do with it? How do we assemble that? And that's up next. So thank you for joining me. And I'll see you in the next one.